Hi everyone, welcome to the conference seminar. And today I'm happy to welcome Daniel. Daniel, he got his undergraduate degree from University of Sao Paulo. He did with a major in oceanography and a minor in physical oceanography. His thesis was about the production of modal waters in the South Atlantic. This was in 2018, right?
Yes.
All right. And after that, he started his PhD looking at abyssal ocean circulation and Antarctic bottom water, also in the South Atlantic. So, Daniel, the floor is yours, and
Okay. Thank you.
yeah, have fun.
Thank you. So good evening, everybody. My name is Daniel, and today I want to talk about what will be, hopefully, the first article of my PhD thesis. Currently, I'm a PhD candidate at the University of Sao Paulo, where I work with my advisor, Olga Sato, at the Laboratório de Oceanografia por Satélites. So, this presentation is divided in 4 parts. The first one, the introduction, where I would like to talk about the AABW. I'll give some characteristics and a definition of this water mass. And I'm going to talk about the AMOC also, the Atlantic Meridional Overturning Circulation. And this is a key point of my PhD, since it's linked to the project called SAMBA. And the main goal of this project is to assess and understand the AMOC along the latitude of 34.5 south. So at the end of this section, I'll show some previous works that served as inspiration for us. So the second part of this presentation will be the data and methods section, where I'm going to talk about the SAMBA-W array, which is maintained by the SAMBA project and from where all this data come from. And I want to talk about the decomposition of the potential temperature trend into the heave and spiciness components. The third section is the results section. And the last section, the take-home messages. Here I show a summary of our major finds. So we found out that the abyssal water are getting warmer and fresher in the Argentine Basin, that the potential temperature trend is more related to the heave than to the spiciness. The AABW is contracting and homogenizing this basin, and also that the local dynamics may influence the trends of this specific kind of AABW. So, talking about the introduction, and before talking about the AABW itself, I want to talk a little bit about the global MOC, the GMOC. And to do so, I chose this figure from Ramstorff 2006, simply because this is a very complete figure. So here we see the upper branch represented in blue, right? The upper branch represented in red, the deeper branch represented in blue, and the abyssal one represented in purple. We also see the locations where these branches are generated. So the deeper branch is generated at the north hemisphere, at the Labrador and at the Greenland seas, while the abyssal branch is generated at the Ross and the Weddell Sea. And as we already know, the MOC is responsible for the transport of salt, carbon, nutrients, and heat all around the world. And because of this is an essential feature to the maintenance of the global heat balance. This figure actually shows the global MOC, but as I said before, our main focus is on the AMOC, the Atlantic part of this bigger feature. So our main interest is on this area. And to assess this area, we used data from the SAMBA array, in specific, the western part of it, the SAMBA-W array. And from this figure, this schematic figure, we expect that the deeper and the abyssal branches cross the array. So to make it clear, I bring another figure from Lee et al. 2023, and this one shows the branches and also which water masses fills each branch. So focusing on the Atlantic Ocean, we see the formation of the North Atlantic Deep Ocean filled by the filled by the North Atlantic Deep Water, and also the formation of the abyssal branch filled by the AABW, the Antarctic Bottom Water. Then I tried to mark the position of our array, and here we see that both AABW and the North Atlantic Deep Water crosses the latitude where we have this array. Here I bring a figure from Vaja et al. 2018. The authors also utilized some data from the SAMBA array. And here I present to you a vertical section of temperature, salinity, and oxygen concentration. At the last panel, we see marked the name of the masses that cross this section. And as we just saw, we have the presence of the AABW, the lower circumpolar deep water, the upper circumpolar deep water, but also the North Atlantic deep water crossing this transect. The authors utilized the work from Orsi et al. 1999 to separate the AABW from the lower circumpolar deep water, and they utilized the neutral density level at 28.27 kilograms per cubic meter. We also can use a proxy to define this boundary, and this is the potential temperature isotherm of 0 degrees Celsius. And actually this is a very accurate proxy, and we can see at this plot the isotherm and the isopycnal are very close to each other, so it's a good proxy. Before this water mass reach our latitude, it has to be generated, of course. So this is the result of the mixing of the circumpolar deep water with the Antarctic shelf water, and this figure from Morozov 2010 shows it. This arrow represents the circumpolar deep water entering the domain of the Antarctic shelf water, and this mixture goes down until the seafloor, forming the AABW. This generation actually requires some conditions to occur. So we may have a large and permanent polynya, strong offshore winds, sufficient platform width, and canyons that allow water to flow from the continental shelf until abyssal depths. If we have all of this, we may form AABW. But these water masses are not formed all around the Antarctica. There are some specific spots that this water mass is generated, and here are the spots: the Weddell Sea, the Pride's Bay, the Adélie Land, and the Ross Sea. Each location generates a different kind of AABW, and the Atlantic Ocean are filled by the AABW that was formed mainly at the Weddell Sea, 6% of it, and the other major parts from the Pride's Bay, 32%. So this is the main source of this specific kind of AABW that we are looking at. Now, talking about our inspiration, the first study that I bring today is the Coles et al. 1996, and the positions of the stations that they used at the work is marked at the figure as black dots, and they found that During 1989, actually the AABW was a little bit cooler and fresher than the AABW during the period from 1980 to 1987. But besides that, they also found that the densest and deepest part of the water column by the first period, so from 1980 to 1985, almost disappeared by the year of 1989. So this results in a warming of the abyssal layers. Hurricane Johnson 2012 studied the volumetric rate of change of the AABW in several basins, and here I highlight the AABW from the Argentine Basin, and we see a contraction of this kind of AABW. Actually, we see a contraction of every kind of AABW that fills all the studied basins, and the authors argue that these contractions may be linked to the slowdown of the bottoming of the southern mock. Also, Johnson et al. 2014 utilized data from 3 cruises from 1989, 2005, and 2014. They assessed the southeast portion of the Argentine Basin, and utilizing this data, they defined the potential temperature trends along pressure levels. So they analyzed the period from 89 to 2005 exclusively, then they analyzed 2005 to 2014, and the last profile in purple is the trends considering the 3 cruises, the entire time series. So they found that during the first period, the abyssal part of this basin warmed, and we can see from, let me point at my head. So from this portion of the profile, right? But if we look to the second period, we see that actually these waters get colder. Look at the pattern here, so it's inverse. And if we look to the entire period, it's warming, but with a slow rate of change if compared to the first period. And this value actually here, the 2 degrees Celsius per year, is very important to us because it will appear several times. So keep that in mind. They also defined the trends of the isothermal heights along potential temperature levels, and by analyzing these trends, they found that the upper layer of the AABW expanded during the first period, and the lower layer of this water mass contracted. But the way to see and to analyze this graph is more or less like this. Like, let's take the upper portion of the AABW, the upper boundary, the 0 degrees level, and this level is decreasing 100 meters per decade. And if we get another level, let's say minus 0.2, this level is decreasing, let me see, 150 meters per decade. So actually what's happening is this: the upper part of the layer is doing this, and the bottom part of it is doing this. So what is happening is expansion of the upper part of the AABW. And by looking at the bottom part of it, we can do the same, like analyzing the same potential temperature level with 150 meters per decade, and let's say, I don't know, like the middle way from this, the minus 0.3, we have more or less 75 meters per decade. So what is happening is this, like the upper parts do this, and the bottom part do this. So we have a contraction of the layer. By looking to the second period, this is more diffusive, but the pattern also exists. Like we know we have this movement and this movement, and then the graph goes there and the graph goes there. It's more diffusive, but it still exists. And by looking to the entire period, we notice the same pattern. So the upper layer expansion of the AABW followed by a lower layer contraction of this water mass. Mine et al. 2020 analyzed the data from the SAMBA array, but they used some temperature sensors attached to inverted echo sounders located at the sites A, B, C, and D. These echo sounders has an hourly sampling rate, and it's important to know that the AABW is restricted to the portion of this section, restricted to the portion between site B and site D. They also plotted the time series from these sensors, along with the temperature measured from CTD casts, and they are quite similar. They are independent data, but they are very similar. So they are similar, and they also defined some parameters. And from this huge table, I want you to look at the trends of the temperatures, focusing on the sites B, C, and D. So the temperature trend are almost the same that I presented to you earlier at this presentation, the 2 degrees per year. Now, Campos et al. 2021 tried to assess the northernmost part of the basin, right, at the Vema channel, and they also found the same rate of temperature change as the previous authors. And the last, Johnson 2022, analyzed data from deep Argo floats and compared with some historical data, and again he found the same rate of change of the abyssal part of the Argentine Basin. So we just saw several studies that corroborate to each other, but still some open questions exist. Like, is the warming uniform in all regions of the Argentine Basin? Because we looked at data from this part of the basin, this part of the basin, and all around the basin. Now we are looking at this part. And also, what is causing this warming? So, thinking about it, we have two hypotheses. The first one, the Antarctic bottom water has contracted and warmed along the SAMBA over the period from 2009 to 2022, and that the recent modulations of the Antarctic bottom water in the northwestern portion of the Argentine Basin are more related to its formation rate than to the change in its properties during generation. So we are trying to figure out what's happening and what's causing this warming in the Argentine Basin. Now about the data and methods. Here I bring to you a figure that tries to summarize some information about the SAMBA array and the utilized data. At the first panel, we see the position of the hydrographic section of the transect, right? And at this transect, the AABW is restricted to the eastern portion, with the isobeth of 3,100 meters as its western limit. From among all these stations, we chose to work with the site BB in green, C in blue, and D in red. And we did it because this site has the greater number of casts among all the sites of the ray. So they are almost annually sampling, as we can see by the time series presented here in the second panel. And it also shows the number of casts that successfully measured the AABW in each cruise. So we have some differences between cruise. So in 2009, 4 casts measured AABW, but in 2022 we have a cruise with 9 casts. The third panel shows the mean potential temperature vertical transect of our study area, and here we defined the upper limit of the AABW using the proxy, the 0 degree isotherm, and it's represented in white. About the decomposition of the warming trend, here I present the approximation of it and how we did this decomposition. So we defined earlier the actual potential temperature trend, and it's plotted in purple, and the decomposition of it in gray is the spiciness, and it's represented in gray, the first term of the equation, and the second term is the heave, and is represented in orange. The sum of these two parts of the equation is the approximation of the temperature trend, and is represented in pink in our article. So we just saw the equation of this. We just saw the equation of the decomposition, but let's see how it is in a TS field, for example. This figure is from Perkin Johnson 2013, and we see that spiciness represents a shift in the original profile. So the blue one is the initial occupation, and the second one, the final occupation, is in red. So we notice a shift in the profile, and heave actually is a vertical movement of this profile. So this is how to visualize these components. So just to make a mental experiment here, for example, let's increase the temperature of a water parcel following fixed depth. So we are moving this parcel in the TS field from 1 to 2. We are doing this movement, right? And we just saw that heave is the vertical movement of the profile, so the movement is this one. And spiciness is the split, is the movement of this entire profile, so the movement is this one. And we saw by the equation that we can sum heave and spice in spiciness. So A is equal to B plus C. And this is important because now we can see that if we increase the temperature of a water parcel following a constant depth, it generates a water cooler and fresher than the previous water following the same density level. I don't know if it's clear, but the point is this parcel is cooler and fresher than the parcel here that has the same density in the previous profile. So this is different point of views of the same thing. So about the results, here I bring the trends of the potential temperature, salinity, and stratification. Now along pressure levels, the shading represents the confidence interval of 95%, and the dashed lines the average position of the upper limit of the AABW. And it's important to notice that this is only a loose estimation. We actually don't know where the AABW is, because this upper limit is changing all the time. So this is only to guide us in our analysis. So, looking at the first panel, we see warming of the waters in the AABW domain. So we can see from the profile here. At all sites, BB, C, and D, the portion of the AABW is warming. And again, the number 2 milli-degrees per year appears at D, and a little bit less at the site C, and the site B has a bigger magnitude. By looking at the second panel, we notice freshening in the waters that fills the AABW domain at the sites C and D, but this is not true at the site BB. Actually, the salinity is increasing in this location. And looking at the Brunt-Väisälä profile, this is more diffusive, but on average, the rate of change of the Brunt-Väisälä frequency is positive on the sites BB and D on the AABW domain. So from this part to the bottom, the average value of Brunt-Väisälä frequency is positive, and from this part to the bottom, the mean value is also positive. So talking about the decomposition, and we needed to try to understand what is causing the warming of the abyssal levels of the Argentine Basin. And looking at it, we notice first that at all sites, heave and spiciness has opposite patterns. So spiciness is negative here, and heave is positive here. The same here, and the same here. So gray and orange are always opposite in the AABW domain. And if we look carefully, we notice that the potential temperature trend is more related to the heave to the spiciness. BB, this is true, like the pink profile is more similar to the orange one. This is also true at site B, and this is also true at site C. I forgot to mention, the dotted line here represents the number of casts that we used at the approximation, and because of the regrading, because to calculate heave and spiciness, we calculate it at neutral densities. To regrade to pressure levels, we lose some data. So our uncertainties are related to this smaller number of samples. So let's return. We notice also that the spiciness is almost uniform, both along the water column and along our transect. They are all the profiles are almost uniform in that sense. But heave displays a notable variability between sites and also along the water column. Well, taking all of it into consideration, we can infer that the warming that we noticed at the previous studies and here also is caused by a decrease in the formation rate of the AABW instead of the changes into its properties during formation. So we speculate that now we have less formation of AABW instead of the same formation but with different parameters. This is what we get from this analysis. Now, to better split the AABW from the LCDW, because at the previous profiles we do not know where the upper boundary of this water mass actually is. We defined the trends of salinity, first panel, isotherm height, and stratification again, but this time along potential temperature levels. So we can use the 0 degrees Celsius to split the water masses. Now I know certainly that all these trends are inside of the AABW. So, analyzing the first panel, what we notice is a freshening of the AABW, and it was already expected, because if you remember, we have a warming trend in all sites following pressure levels. So it is expected that this warming trend leads to a freshening following temperature levels. Again, in accordance with the work from Johnson, we have an expansion of the AABW followed by a contraction of it in both sites D and C. We do not have this pattern at the site BB. And we notice in homogenization of the AABW again at sites B and C, and a positive rate of change of the Brunfeld frequency at site BB. And I forgot to pass. Okay, here I'll try to explain this the better way that I could. I don't know. This figure is just to rectify our calculations and statistics. So here I bring to you time series. So this is time from violin plots, right? The first line is the time series of violin plots of temperature, and the second line of salinity. So violin plot is a plot which unites both box plot and histogram. So inside of each histogram we have a box plot, and we choose to work with a violin plot because, as we can see, the distribution of the temperatures inside both temperatures and salinity actually inside the AABW are not normal. So it is better to work with a median than to using a mean. But well, the point here is to ratify our finds using the calculations. And from the temperature at site D, for example, we notice an increasing temperature as time goes by. As we can see this because the violin plots are going up. And we also see that the bottom part of it, which used to be colder and homogeneous, now is less cold and less homogeneous, as we saw at the Brunfeld frequency trends. So this is a graph only to rectify our calculations, to make it easier to see these trends that we are talking about here. Well, we talked a lot about trends, and we know that we have some differences between locations, like they are not uniform along all the transect. Like site BB is a little bit different from site C, and C is different in comparison to the site D. And we believe that these little differences are results to the local dynamic impacts of the study area, right? So, thinking of it, we plotted the V and U components of the velocity measured by LADCP. So the profile shows in gray each velocity profile, and the colored profiles are the means. looking at the first and second panels, we notice that actually site PB is located within the DWBC domain, and we can say this because we have some negative velocities at this profile. And we also see from these plots that the zonal component of these velocities are more variable than the meridional ones. Some previous studies already argued that these differences between the velocities at each site are due to the passage of deep eddies along this transect and Rossby wave and topographic Rossby waves. So as take-home messages here, the first one is that the abyssal waters in the northwest portion of the Argentine Basin predominantly experienced warming, freshening, and increasing stratification during 2009 to 2022, in agreement with the previous studies. Now, we speculate that the variation of the potential temperature at abyssal depths reflects the lower rate formation of the AABW. So this warming is a result of less formation of the AABW, and that the AABW layer experienced freshening, fining, and a decrease in stratification, remembering that the local processes could be extremely important to the variability of such properties between the locations. So that's why we have these differences between locations. And that's all. Thank you very much.
Thank you, Daniel. Any questions? Sure.
Hi, Daniel. Can you go back to your second point of your conclusion?
Yes. Oh, sorry.
You said that the variation of the potential temperature abyssal depth reflects the lower rate of AABW formation. Can you explain again how you came to that conclusion? I'm not sure I followed.
Yes, actually, this is a speculation, right? We are
It's a
not.
speculation.
Yeah, we are not looking at the Antarctica, for example. We are looking at very northward transect. By the decomposition of the trend, of the potential temperature trend, we see that this potential temperature trend is more related to the heave component.
Okay.
And this leads to this assumption. Because if the spiciness is the preponderant one, it should be the like, I don't know how to speak this. If spiciness was the most important, probably the same amount of AABW are generating, but with different characteristics, temperature or salinity, for example. So we are speculating this.
Yeah, I think I understand. Can you show again the trends of
Yes.
heave and spiciness? Okay, that's it.
Yes.
Okay.
Because of the
Okay, the green one is the spiciness. Is it green? Which color is it? I can't
gray.
see.
It's gray. This.
Okay. And so what does that mean that it's negative?
It's negative. That
That the spiciness is decreasing?
spiciness is trying to push the temperature toward the negative values.
Okay. Okay, I'll have to think about it.
It's essentially spiciness shows the temperature changes along isopycnal surface.
Let me
Yeah.
show
So
Yeah.
the
it's
equation.
if it's cooling to
Yeah.
keep the salinity to keep the density constant, we need to have cooling. So it's
Yeah,
freshening. Sorry.
Yeah, I was trying to
Freshening,
think of
it's cooling,
what the sign means. But
Yeah,
okay.
exactly. So
Yeah.
if you see a negative spice, you're seeing freshening,
Yeah.
essentially. Right?
Yeah. I think looking at the equation is better just to the graph. So
I don't know. I'm not sure. Okay, thank you very much.
You're welcome.
Any other questions, Danielle? No? Okay, so I do have a question. So you're talking about local dynamics, right?
Yeah.
One thing is, well, you also,
Yeah.
you're talking about local dynamics based on the differences in heaving,
Yes, yes.
correct?
Mm-hmm.
So what you can tell me about why we expect the local, depending on where you are, the heaving to be different? Why is that? Because the spiciness seems to be pretty consistent everywhere,
Yeah.
but
So-
the heave changes a lot.
Like it was speculated that some eddies passes along this transect, right?
Mhm.
And the isotherms should go ups and downs. And by heaving, we are looking exactly like this. It's the capability of the isopycnals doing this. So if we are looking at if our cast captured the water inside an eddy, for example, this may be a bias of in our trend, for example.
Okay.
So maybe, we don't know, this difference could be related to the passage of these eddies or whatever they are, these features passing through along the ray.
Okay, and what about the local stratification? If you look at site BB, which is closer to the continental slope, upper continental slope, and all the way down, have you looked at different stratification? So let's say if Raspberry wave is coming westward, right?
Mhm.
It's going to oscillate if the isopycnals on one
Yeah,
side, and maybe it doesn't get all the way in, or
Mhm.
there's also meanders of the deep western boundary current, right?
Yeah, and
But do you see, like, in terms of stratification, do you see like changes, like separation of the isopycnals, or you haven't looked at it?
no, I haven't, but this profile shows that the site BB is actually more energetic than the other two.
Mm-hmm.
Maybe because it is at the boundary of the DWBC domain.
Mm-hmm.
I don't know, but the point is that the site BB is quite different from the other two.
The other two.
Yeah.
Cool. Lee?
Hi, Daniel. Good job. I have a question. So, if the formation rate of AABW decrease, does that mean there are less cooler water formation from the polar region?
Yeah, in that sense, yeah.
Less. So, if there is less cooler water formation, does that mean the spice component will show the warming trend?
No, then the heave component will show this. Because if we have less water with cold temperatures, for example, if at time 0 we have this layer, at time 2 we have this. So we see a temperature change in this area. So this heave show this decrease of the isotherms, right? Otherwise, we see the same amount of generated AABW, like the length of it is the same, but what we are changing is the temperature. So Spice will show this. I think so.
Thank you.
Any other questions? No?
So these sites, are they the same sites as the CPIs that Chris Minen looked at?
Yes, the same size, and the temperature trends are quite similar because they looked at the very bottom part of
Yeah,
the
I know the paper, yeah.
yeah,
Read it, yeah.
and you're looking all through the water column.
All right. Thank you all for coming. Let's thank Danielle again for the presentation. So before we go, just Danielle will present this part of this work at Ocean Science Meeting. So if you're there, please check it out. And if you want to discuss more about his results over a beer there, that would be awesome. All right? Thanks, everyone.
Thank you.
Thank you.